call it the input transducer. And a transducer is a device that converts a non-electrical input into an electrical signal, or the other way around. Okay, so it can turn a non-electrical input like pressure, temperature, anything like that, or sound into an electrical signal. And it can also do the opposite. So in an output transducer, it's going to do the opposite. The electrical signal will be going into the output transducer, and the output transducer is going to turn it into like light or sound, anything that is not an electrical signal.
I think she got disconnected somehow. Wait. Hello. Yeah, Sundus ran into some problem. So let me summarize what she was just talking about. So any electronic system has three parts. Okay, three parts: an input sensor, processor, and output transducer. Okay, remember that transducer is anything that can change one form of energy into another form. Okay, we also have transducers in our bodies, such as the eye and most of our sensory organs, especially the receptors. Like, for example, let's take the example of eye. The light energy is converted into electrical impulses or electrical energy in the nerves. These nerves are connecting the eye with the brain. That is one example of a transducer. So remember, transducer is anything that converts one form of energy into another form of energy. And in case of electronic devices, it is usually the input will convert the changes in the environment into an electrical. Again, this will behave exactly the same way as the sensory organs of our body. The changes in the environment are converted into an electrical signal, such as a change in temperature, such as a pressure, okay, change in pressure. All these are changes in the environment, and they will translate into an electrical signal. That electrical signal will then reach the processor, and then output transducer. Now this again is a transducer. So again, this is converting. Now this time it will be converting the electrical energy into a mechanical motion. For example, like you have generators. Generators, they convert the electrical signals into kinetic energy. The machine starts rotating. So that is an example of an output transducer. Okay, so output meaning it converts or it translates the electrical signal into some sort of motion or in some physical form. It can be in the form of light emission. It can be in the form of rotation of the machine, or even sound, or so this is the basic this is the basic, you can say, the outlay of the electronic system, right? They have given a few examples here. Examples of input sensors in the electronic systems are LDRs, light dependent resistors. Now, as the name suggests, it is a resistor. Okay, in order to understand this chapter, you have to know the basics of electric circuits, meaning you should know how electricity behaves, and what is a resistor, what is resistance. You should also know what a potential difference is, what a voltage is, and how the potential difference is related to resistance and all of that. So I'm assuming, though I have not covered that part of physics with you, but I'm just assuming that you know that already. And if you don't know it, then you'll have to tell me. You'll have to, you can ask, and then we can summarize it for you. Okay, so light dependent resistor is an example of an input sensor. So the name suggests that it is a resistor, meaning it has resistors have high resistances. What is resistance? It does not allow the current to flow smoothly or easily. Okay, and in doing so, when the current is trying to force its way through it, the electrical energy is converted into heat energy. Okay. Okay, now Sundus is taking over from me. So start with the examples of input sensors. Okay, Sundus? Okay, Sundus is taking over from me. The reason I'm asking Sundus to teach this chapter is because I think she is better at this than me. I am not that good at this. Okay, so let's see. Okay. Okay. Okay, Sundus.
Can you guys hear me?
Yes, we can hear you.
Okay. Okay, so
But we cannot see the whole page of the book. So if you can arrange the book.
okay, sure. Just a sec. Just give me a second.
Okay, so light, let me, while she is fixing, let me talk about the light dependent resistor. So resistor, I told you, has high resistance. A resistance meaning that instead of allowing the current to flow through it smoothly, it faces resistance. And so a lot of its energy is converted into thermal energy while doing so, while trying to pass through the resistance. A lot of electrical energy is converted into thermal energy, that thermal energy which is not usable. Just like you have friction, you know, when the more friction you have, the more thermal energy is released. So similarly, when the current is trying to pass through a high resistance resistor, its energy is converted into thermal energy. So light dependent, meaning that its resistance is dependent upon the light. So as the light falls on it, the resistance decreases. Now, most of these light dependent resistors, or even these diodes, they are made up of semiconductors. What are these semiconductors? Remember chemistry, metalloids, which are in between the metals and the non-metals. Okay, those are called metalloids. The reason why we call them metalloids is because in certain conditions, they behave as non-metals and they become insulators. And in other conditions, they behave as metals, and so they become conductors, because metals are good conductors. Okay, so they choose this metalloid. So we won't go into the details of how these diodes work and what are these diodes made up of and all of that. But just understand that in certain conditions, they behave as metals, and in other conditions, they behave as non-metals. Okay, and okay, Sandoz, take over.
Okay, so till where did you cover?
Yeah, I was just talking about LDRs. So talk about give them an example of examples of input sensors, examples of processors,
Okay.
and output transducers, and then you follow the sequence of the book.
Okay, so like I told you, the input sensor detects changes from the environment and converts them into an electrical, like electrical impulse, you can say. So they can include anything like LDRs, thermistors. They're like depended on temperature, microphones to take in audio and then turn it into like electrical impulses, and then switches, and then pressure sensors, anything like that. And a processor is what processes the input that the input sensor gives in. So it processes and decides and turns it into a signal that the output transducer can then work on. So if, for example, we're talking about a mic which is connected to like a loudspeaker, so if you have a microphone and that takes in your audio, turns it into an electrical impulse, the processor will change that electrical message for an audio into a sound, right? That is going to be going out of the loudspeaker. And then that signal for the sound is going to go to the output transducer. And the output transducer is going to give us our sound. Your sound will be heard through the speakers. So processor decides on what will happen to the input. Then the output transducer converts the electrical energy supplied by the processor into any other form. For example, in alarm clocks, it turns it into LEDs, light. And for loudspeakers, like the example I just gave you, it turns it into audio. Motors, kinetic or thermal energy, heaters, thermal energy. So in all of these, you can see that the electrical energy is getting turned into any non-electrical form of energy, any physical form of energy. So over here, they have given an example of a radio. The input sensor is the aerial. So this is what senses it receives the radio waves, right? And then it sends it to a processor in the radio, and then the radios amplify the signal and then change it into any other physical form. So in this case, a loudspeaker so that you can hear the news, right?
So I think that the radio waves are detected by the aerial and then maybe, yes, and then converted into an electrical signal. Okay, and we will
Yes.
use the word, and in physics we will use the word signal. Okay, impulse is for biology. Okay, so
Yeah.
yeah, okay, so radio waves are converted into electrical signals in radios. That electrical signal reaches the processor. The processor amplifies it. Do you understand the meaning of amplify? What does amplify mean? Amplifying the signal?
Increasing it, yeah, in
Right.
size.
Yes. Increasing by a certain ratio, increasing it, enlarging it. So amplifies the signal, and then the output is the sound that we hear. So it's a sound energy. The output is the sound energy. So we have transducers at the entry and at the exit, input and output. These are the two. And in the middle, we have processor. Okay.
Okay. So then on the next page, they're talking about input transducer. So they're talking about the first part of the electrical system. So over here, they're talking about light-dependent resistors, or for short, LDR. So the action of a LDR depends, as you can see from the name, on light. So it's dependent on light, and it obviously is a resistor. So it is made of a semiconductor, cadmium sulfide, and the resistance of cadmium sulfide decreases as the intensity of light falling on it increases. Okay, so that means more the light, less the resistance of the LDR, and so more current can pass through it. Okay, so
Now,
they are
if anybody has this question in mind, that why does this happen? Why is it that when the light falls on it, the resistance decreases? So for now, at this level, when we are not going into details, just know that, as I told you, they are made up of metalloids, and so they are conductors under certain conditions and non-conductors or insulators at other conditions. So this cadmium sulfide, and I cannot remember if cadmium, I don't know what cadmium is. I think it's a transition metal. I don't know.
no, it's a metalloid, I think.
Yeah, okay. You can check the periodic table and see where it is. Is it a metalloid? Usually they are metalloids. Okay, and so when the light is falling on it, what's happening? Its resistance is decreasing,
Decreasing.
right?
Yeah.
Yeah, so it's becoming a conductor. It's becoming
Yeah.
a conductor. So yes, in the presence of light, it is a conductor, and in the absence of light, it's not a conductor. So that's how it's behaving. Okay.
Yeah, so the LDRs are used, first I was really confused as to the practical application of LDRs, but they are used like widely, like on your phones for auto brightness. So when the sunlight is really, really high and the screen gets really dark, that's when the LDR detects it. And so the resistance decreases and the brightness of your screen increases so that you can see it. The opposite happens in the night. There's no light on the LDR, and so the resistance increases. That means less current is flowing through the LDR, and so the brightness of your screen is lower because you don't need that much brightness, right? So over here in figure 41.3c, they are showing how an LDR is hooked up to a relay. Okay.
Can you zoom in? Can you zoom in on this diagram, figure 41.3?
Sadly can't zoom in more.
Oh, okay, okay, okay. Yeah, it's fine.
Can you guys see it better now?
Yes, yes, we can.
Okay, so in the diagram in figure 41.3c, you can see a LDR hooked up to a relay, and a relay they are gonna mention later on, but a relay is like two circuits joined together, not with wires necessarily, but like with an electromagnet. Okay, so over here we have an LDR and we have a resistor here, and then we have this power source, right? Battery. We have a bell and a relay. So this, I'm guessing, is a electromagnet, right? This is a switch. Okay. So LDR, now you do know that as the light falling on it increases, the intensity of light increases, the resistance of the LDR increases, right? And now you can see that there are two resistors on one wire. That means the resistance is going to be, the potential difference, that is the voltage. So voltage and potential difference are the same thing, right? So potential difference is like the difference in charge. So like the potential difference is gonna be the difference across this battery, because we have positive on this side, negative on this side, right? So the same thing for this wire. So we have positive on this side and we have negative on this side. Okay, and so the voltage is divided across these two resistors. So this is acting like a potential divider because it's dividing the potential difference, right? So
Okay, and to understand this circuit, you need to know the basics. You need to know the voltage. What is voltage? What is potential difference? Okay, and how the current flows, and what are the rules that the current follows when it flows through the circuit. So I hope everybody is aware. Everybody knows what a potential difference is. Can anybody really quick recap what a potential difference is, so that I know that you know? Do you understand what potential difference is? Just rough idea. No need for proper definition. Just a rough idea. Cannot see any raised hand. Okay, Abdurrahman. Yes, you can unmute.
Ma'am, potential difference is like charge carriers, like which carry charges, positive and negative,
Okay.
or difference of 1 volt of energy, like in equals to 1 joule of energy.
Yes. Yes. Joule is a unit of
Uh, Coulomb, volt,
no, wait. No, I'm asking joule is a unit of what?
energy.
Yes. 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 So yes, you have a vague idea. See, potential difference is the difference in the energy which is possessed by 1 unit of charge, and 1 unit of charge is 1 coulomb. So potential difference, you can think of potential difference. See, Yeah, we'll have to go into the basics of circuitry if we go into that, and we don't have time. We want to cover 2 chapters. So I'm just assuming, so just look at it as energy, potential energy, by the way, not kinetic, okay? Potential energy. That's why we call it potential difference. So it is the potential energy, the difference in the potential energy of the charges between the 2 points. That is called the potential difference. So difference in the potential energy possessed by the charges at 2 different points. That is called potential difference. Did you understand?
Yes.
Yes, hopefully you understood. If there is anybody who does not understand potential difference, then that he will face problem. He won't understand this chapter then. Okay, so if there's anybody, please let me know. Okay, Sundar, go on. So the potential difference provided by the battery is 6 volts. That will be divided into that resistor and the LDR, right?
Yeah. So
Okay.
so it is like so because they are connected in parallel, that means that we have a 6-volt potential difference on this wire and this wire, right? All these wires in between, right? So we know that 6 volts is the voltage that is being divided between the resistor and the LDR. And so that means that as the light intensity that is increasing, the resistance of the LDR is decreasing, right? And when the light intensity is decreasing, the resistance of the LDR is increasing. So let's suppose we have lots of light. Okay, so light intensity is increasing and the resistance of the LDR is decreasing. So there is less resistance in the LDR. That means there is less potential difference across the LDR. So we're not talking about any other element of this circuit. We're just talking about the LDR. So there is like less difference in charge across this LDR, right? Because most of the current is flowing. Think of it as a pipe, right? So because the pipe is wider, we don't have much of a crowd on each side of the resistor, right? Or the gate in the case of in the pipe example. Okay, so because the potential difference is less over the LDR, the potential difference over the resistor is more, right? Because this
You
voltage
mean
is gonna get,
across the resistor? You mean across
yeah
the resistor,
yeah yeah
right?
yeah 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 yeah. So across the resistor is more because 6 volts is being divided over both of these, right? So because the resistor's potential difference increases over the resistor, and because this relay, or just talking about this electromagnet, which is connected in parallel to this resistor, is going to be the same. So let's say that 5 volts, we have 5 volts
Okay.
here.
Okay. Does everybody? Okay. Tell me something. If the resistance increases, what happens to the potential difference? What happens to the voltage? I'm
Decreases.
asking. Yes. Sorry.
Decreases.
Decreases. If resistance increases, what happens to the voltage?
It increases.
It increases. If the resistance increases, the voltage increases. And why do you say that? Why? I mean, I want to know the reason. Do you
Because
know
they
the
are
reason?
no.
Yes. Remember that, I mean, we will not go into the details of reasoning, but I mean, at least you should know that formula, V is equal to IR. Remember?
Yes, yes.
Right. V is equal to IR. So this can you write it? Can you write this formula? This equation? Yes. So when the resistance increases, what do you think will happen to the voltage? They are directly proportional, right?
Yes, it increases.
Yes. So resistance is directly proportional to the voltage. So if resistance increases, the voltage should also increase. So when the light is falling on the LDR, the resistance is decreasing. When the resistance is decreasing, the potential difference is also decreasing. But remember, the potential difference provided by the battery is constant, which is 6 volts. So if the resistance across LDR decreases, then the other resistor, which is connected in series with it, will get the brunt, the larger portion of the potential difference provided by the battery. Okay, so this can you give us some examples, numerical examples, right? For
Yeah,
example,
so that's what
yeah.
I wrote. I wrote 5 volts for this resistor and 1 volt for the LDR.
Okay.
So if we add that up, that gives us 6 volts, right?
Right.
So,
Like for example, before the light fell on the LDR, the potential difference was divided equally, 3 volt, 3 volt.
yeah.
Right? For example, 3 volt. Can you please write a little darker? 3 volt, 3 volt. Yes. And now when the light fell on it, the resistance decreased, and so the voltage decreased, and now it decreased from 3 volts to 1 volt. So now automatically the other resistor the other resistor's voltage increased to 5 volts because they have to sum up to 6, because that is the voltage provided by the battery. Okay, so can you see now that the voltage across the resistor has increased to 5 volts. Okay, now Sundar. So then now you can see that the relay is parallel, is connected parallel to it. And remember,
Yes.
one of the rules of the circuits that the devices which are connected parallel have the same voltage. So if the
Same
resistor,
potential difference.
yeah, so the resistor, if it has 5 voltage, the relay should also have 5 voltage across it because it is parallel to the resistor. Yes, Sundos, and then?
Yeah, so if this has a potential difference of 5 volts across it, the electromagnet is going to have a potential difference of 5 volts too. And if this electromagnet reaches the potential difference on which it works, so the potential difference that activates it, that makes it magnetized, right? It's going to pull this piece of metal. So let's say that the potential difference on which it gets magnetized is 5 volts. So now that the circuit has reached 5 volts, that means that the resistance of the LDR has dropped to a level that this other resistor now has a potential difference of 5 volts, right? And so this gets magnetized. This pulls the switch shut, right? Because it's now acting like a magnet, right? And then the bell starts ringing. So that's how the LDR is working in this relay system. And I am going to explain relays in more detail as they come later in the chapter. But right now we're going to move on to thermistor. Just a second.
Yeah, okay.
Okay. So a thermistor contains semiconducting metallic oxides whose
we cannot hear you, Sundos. Your voice vanished. Sundos, we cannot hear you. We cannot hear you, Sundos.
Can you hear me now?
Yes. Yes.
I don't know, there's something going on with my Wi-Fi. Okay, let me see. Okay. Okay, so the thermistor's temperature might rise because it's directly heated, or because a current is passing through it, or because it gets heated up because a current is passing through it. Okay, so this is a symbol for a thermistor, and a thermistor. There are lots. You know, there are different types of thermistors. Yes.
Yeah, and a recap that what is a thermistor? It is a resistor, the resistance of which is dependent upon the temperature. Therm comes from thermal. Yes, so remember it that way. Temperature affects its resistance. So it is a resistor, the resistance of which depends upon the temperature. So as the temperature rises, what happens?
The
So its
thermistor
resistance
its
decreases.
resistance decreases.
Yes, so it is a conductor at high temperature, right? Yes.
Yeah.
It's a conductor at high temperature. Okay.
Okay, so if you heat a thermistor up with a match, or because it gets heated up in a circuit, both ways it is gonna the heat is gonna decrease its resistance. So there are different types of thermistors, one which is fixed, okay, and one that can vary. So you can vary the levels at which the temperature will have it decrease its resistance. So let's say at one, so I have a knob, and if I move the knob, so let's say I have a slider here, okay, and over here, the resistance increases and the resistance decreases as I move the slider to this side, right? So I can vary the temperatures using the slider. I can vary the temperatures on which this thermistor will get activated. That is, it will decrease its resistance, change its resistance in any way, okay? So this is used in thermometers, right? So a different thermistor for each degree, you know, to like mark whenever, for example, 30 degrees Celsius is reached, the thermistor's resistance decreases, and so the current passes through it, and the bulb lights up, telling us that it is 30 degrees Celsius. Okay. Um, So it can also form part of a potential divider across a DC source. Again, it is hooked up to a relay. It's performing the same job as the LDR did in the other circuit. Again, the potential difference is getting divided between these two resistors, okay? But the only difference is now the resistance is not fixed. I mean, even in the LDR, the resistance was not fixed. It was depending on the light. Now it's getting depended on the temperature, right? And as the temperature increases, the potential difference for this resistor increases across this resistor increases because the resistance in this thermistor decreases. That means the current can flow through it easily, right? So less potential difference across this thermistor. The 6 volts, most of it is going to get uh, handed off to this resistor, less of the potential difference to this thermistor because of the less resistance. Again, this electromagnetic coil is going to get magnetized, and it's going to pull the switch closed and the bell will ring.
Okay, another thing that you must have done those electromagnets in chapter 43, which we haven't done yet. So, but you understand that when a current flows through a conductor, it gets magnetized, right? It behaves like a magnet.
Yeah.
And so, yeah, so there is a electromagnet inside the relay. And so when the current passes through it, it turns into a magnet and it attracts that arm of the circuit. And so the loop closes and the current flows through it. And therefore the current reaches the bell and the bell rings, right?
Yeah.
Another thing also, yeah, and Sundus also explained in terms of this equation, V is equal to IR. So when the resistance is decreasing, the voltage is decreasing, and so the voltage across the other resistor is increasing. Also remember that the relay requires a bigger voltage. It requires a bigger voltage to operate. So only and only when the voltage across the resistor across which it is connected is big enough, only then it will operate. Are you guys understanding? Is there any question? Please do ask. So both the circuits that we've done so far are almost similar. The only difference is that one we had in one, the voltage was being shared by LDR, in the other voltage shared by thermistors. So one is dependent upon light, the other is dependent upon the temperature. Is there any question? Please go ahead and ask. I want to know if you want to. Okay, Sundus, carry on.
Okay. So, yeah. So, and also one more thing, just because the symbol for the thermistor has this kind of thing that resembles a slider doesn't mean that each thermistor can be varied, okay? So if we have a variable resistor, only then can the temperature at which the alarm sound can be varied, okay? If it's a fixed thermistor, it until and unless the question doesn't say that it is a variable thermistor, do not assume that it is variable, okay? It's just fixed. Okay, so now we're going on to the next part of the electronic system, which is transducers. So they decide what happens to the message that is sent to them. So relays.
Okay,
So,
okay. This variable resistor thing that you discussed, it is so that we can control the temperature at which the alarm sounds.
yeah.
Right. So if
Yeah.
so if you want the alarm to sound at like for example 40 degrees Celsius, you don't want the temperature to go above 40 degrees Celsius, so it will go off only at 40 degrees Celsius, not at 30, not at 20.
Yeah.
Right.
Yeah.
This is the
Yeah.
idea. Okay.
Ma'am,
Okay. Let's start the relays.
ma'am,
Yes. Yes.
I created one fire alarm using the same
Yes.
thermistor. If in case the fire like
Oh,
gets lit up
good
at
job.
50 degrees, I still have it. Can I show it to you?
Yeah, sure.
Okay.
You'll have to share your
One sec.
video, I think.
This was a fire alarm I created in grade 6.
Oh, wow.
Here is
Wow.
the thermistor.
Okay. So
One sec.
what substance did you use? I mean, what material have you used?
I broke this off a tube light, this
Okay.
thing, and I use a circuit.
Yes.
I used one speaker, a 9-volt battery. That's it.
Okay. Wow.
Oh, wow.
In grade 6.
Yeah,
Yeah, that's really
I was
commendable.
in grade 6.
Yes, that's really commendable. I just hope that we all try to become something when we grow up, right? And I love electrical. I mean, I'm not good at it. I'm not good at it, but I really envy people who are good at this electrical physics. I'm really impressed by them. Okay, Sandas, let's start the relays.
Okay, so a relay is like two switches connected with each other, but the main reason we use a relay is for better control and for safety. Okay, so in this, so I'm going to use this to explain relays. Okay, this diagram. Just ignore this. Okay, so this is our appliance that is hooked up to the main supply. Okay, and then we have a switch right here, and we have electromagnet here, and we have output of switching circuit here. So this confused me for a long time, but by switching circuit, they mean a circuit which has a switch attached to it, so that you can control it, right? Because the purpose of this other circuit is for control. So if I complete this circuit, I'm gonna have a switch attached to it or a battery, okay? I could even have a battery here. Let me add a battery here. Okay. So now we have the circuit complete, so now it's easier to understand, right? Oh, okay, sorry. They already do have a switch here. Okay, so I'm just gonna make a battery here. Okay. Okay, so this is a circuit that you can switch on and off, right? And this relay is made so that you can control the appliance, right? So the reason why this is made is because when this appliance will not run until this circuit is closed, right? But this circuit will only be closed when this circuit is closed. Why? Because when you close the switch, only then will this electromagnet start working, right? And it
Right.
will get magnetized, it will attract the switch, this switch will shut, and this main supply can then this other circuit can finally be complete, and that's how your appliance will start working. So what this does for us is that it does not put us into direct contact with the main supply, right? So if we're working on any of these wires, we will not be shocked, right, or electrocuted. And also it gives us better control without endangering us.
Right. So its purpose is safety. And so you have one electromagnet which will turn into a magnet, and it will attract that arm of the relay and close the loop of the which is connected to the main supply. And so the appliance will have the current passing through it, and therefore it can work, right?
Yeah.
Okay. Okay. Is there any question? Is there anything that you want to ask? Okay, let's move on to light emitting diodes.
Okay, so this is what is really widely used nowadays, LEDs. So it is a diode, and a diode is a electronic component that makes sure the current flows in only one direction. So this component can always be either forward biased or reverse biased. And what I mean by that, forward biased is, let me show you. So one more thing, this is very important. Okay, where you see this band is where the cathode of this LED is, and where you do not see the band is where the anode of this LED is. Okay, and so when we hook it up to a circuit, it only makes sense that the positive side is going to be with the negative, right? So that there's better flow of electricity, and the negative side is going to be hooked up to the positive side of the battery so that the current flows smoothly and there is attraction between the charges, right? But if
Right,
you hook,
because the current flows from negative to positive,
yes,
right? Also talk about cathodes and anodes a little bit. Are these the same as we had in the electrochemical cells in chemistry? Cathode
I,
is negatively
I have,
charged and anode is positively charged.
yeah, but I have no idea if they perform the same function, but yes, they do have the
Yeah.
same charges.
Yeah, actually, these diodes and these transistors and all these semiconductors, there's chemistry involved behind their working. So we are not going into the details. We will just learn their function in the circuit for now, and also clarify a little bit about the forward and the reverse biases.
Yeah, I'm going to. So basically, this is forward biased if we look at the conventional current. So the conventional current runs from the positive side of the battery to the negative side, right? And this looks like an arrow, sort of. And this is pointing us towards the negative side of the battery. And so this is forward biased, keeping in mind the conventional current. Okay, so you always have to keep in mind the conventional current when you're dealing with circuits. And if we hook it up in the opposite directions with the band here and the arrow pointing in that direction, that is going to be reverse biased, and the LED is not going to work when it is in the opposite direction, when it's facing in the opposite direction, when its anode and cathode are not linked properly. Okay, and if
So
when it is reverse biased and then we have a huge voltage or a huge current pass through it, it might fuse.
okay, so you mean to say that reverse bias is when the positive of LED will be connected to the positive of the battery,
Yes,
and the negative of the LED will be connected to the negative of the battery.
yeah,
That we will call reverse bias. And
yes,
so there will be no flow of current.
yes.
Okay, okay, and also I hope the participants know that what the conventional current is and how it is different from the actual current. You guys know, right? Can anybody tell me the difference real quick, vaguely? What is the difference between the convention current and the actual current? Yes, yes, Zainab, Ajwa, Laiba, anybody? What is conventional current? Okay, Sundus, you tell us.
So the conventional current is what they used to think that the positive charge would flow from the positive side of the battery to the negative. But
Right.
in real now we know that the electrons are the ones that move from the negative side to the positive side, but it makes it easier to understand it the other way around, I guess.
Yes, yes, yes. So before the electrons were discovered, they thought that it is the positive charge that is, for some reason, I don't remember the history, but for some reason they thought that the positive charge, I mean, they could detect the flow of the positive charge, so it was easier for them to follow it. And so, because the electron is negatively charged, so it is actually the electron flow. Later on, they discovered it's the electron. So therefore, the direction of the actual current is opposite to the direction of the conventional current. Okay, so just remember that conventional current is opposite to the actual one. Okay, just remember that much. So this positive and negative that we mark on the circuit is conventional, right, Sundus? Am I right?
No, it's the actual thing.
Okay, yeah, okay. So the terminals are actual, but the arrows that you have marked
Are
on
conventional.
they are conventional.
So
Okay, I'm not.
basically, just keep in mind that everything is gonna be the same. So battery, if I was to make a real model of this diagram of this circuit, the positive side would be here, the negative side would be here. And though I know that the electricity is flowing from the negative side to the positive side, just on my diagram, I'm gonna mark it the other way around. So positive to negative. Always make your
Right.
arrows from positive to negative.
Okay, and so this symbol of LED is also following conventional
Yeah,
current
yes,
direction.
yes.
Okay, so it looks like an arrow, and this arrow is in the direction of the conventional current, right?
Yes, yes, yes. And
Yes.
only when it is in the direction of the conventional flow will it work. If it is in the other direction, it might fuse.
Yeah, so that's called reverse bias. This is what we
Yes,
mean
yes.
by forward bias. And forward bias is like negative attached to positive, and uh, yeah, and the reverse bias is negative attached to negative. Yes, yes, Abdul Rahman.
Ma'am, this the thing you told right now, reverse and forward, is with everything,
No. Just LEDs.
because
Just
I had
LED,
a
right?
no, because I had a like exhaust. We can put it
Okay,
anyway, and the LEDs would work in it.
okay.
Like if you plug a exhaust the wrong way, it would work as a fan, and if you put it the correct way, it would work as a exhaust.
Yeah.
Oh, okay. Then it might have a motor because LEDs are specifically only lights.
I have no idea about that, Abdul Rahman. As I told you, I don't know.
No, so this is only with LEDs. Don't bring other components of the circuits in it, like motors or, other stuff like that. Just don't confuse it with that. Because look,
Okay,
anything that has a cathode and anode is the only thing that's going to have this problem. The other things, you can hook them up any way you like.
okay. And only semiconductor diodes have cathodes and anodes, right?
I am not sure about that. But I am sure that anything that has cathode and anode, that has this problem of forward and reverse bias, but I'm not sure which components have a cathode and an anode.
Okay, okay. Let's move on.
Okay, so one more thing before we move on. An LED is basically made of a very thin wire, which very thin wire, that means very high resistance. That's why they light up. That's why even a slight increase in the voltage or current is gonna make it fuse. That's why it is very important that we use a resistor in series with a LED, because that makes it safer, and an LED will fuse at any voltage higher than 5 volts.
Okay, so this resistor does not allow the current to directly fall on the LED and fuse it.
Yes,
So it like
kinds of,
slows it down.
yeah, softens the impact.
Right. Yes, Abdul Rahman. Yes.
Ma'am, everything she said was right, but like the thin wires LED has, but I'm still confused about the wires she said, because I have a LED in my room and I can plug it any way I want and it lights up.
Yeah, I have no idea about that. I told you
I
I
might
don't
be
know.
wrong. I might be wrong. You can go research.
Ma'am, I'm talking about this one, like these LEDs. It has small
You
strip
know,
of wires,
guys and
single
boys,
ones.
they are better at electrical physics.
No, I'm
Yeah.
just trying to like
Yeah.
clarify my
Okay. So
confusion.
yeah. Find out the answer and share with us as well. Find
Okay.
out. Google it. Search it. Search about it. Okay. And then share with us if you find anything interesting.
Yeah, and
Oh,
there are all sorts of LEDs, especially now, but we're talking about this
yeah. This
one.
is the basic. I think this is the basic. There
Yeah,
are so many advanced stuff now these days. Just we are only trying to understand the basics. This is
No,
just
ma'am,
the
yeah.
ABC.
I am also talking about the basic one because it has like nine resistors marked
Okay.
R9, and anode cathode it has everything marked. I hope like you guys can see it. If I can you see the resistor in the between in the center?
Yes.
Yeah, yeah.
Yeah. And also, they have different values at which they work, in which they work. So I don't know.
I have
They
no
have different.
idea. You find out and tell me too.
Okay.
Okay. Okay. Let's move on.
Okay. So these LEDs are also used at in calculators, alarm clocks, different things on cameras, stuff like that. Okay. So now we're gonna talk
Since we cannot hear you.
Can you hear me now?
Yes. Yes.
Oh, okay. Okay, so what I was saying is that LEDs can be used on radios, clocks, calculators, mobile phones, computers, anything. Uh, no. Just a
And
second.
their function is, what do they do in calculators?
They
They
display the number. The
they
numbers are
display the number.
calculations.
Okay. They display the
Yeah,
number. Okay.
they're mostly used for like display.
Okay.
I mean,
Okay.
just in a camera, for example, the red light that turns on telling you that it's recording.
Okay. Okay. Let's move on.
Okay, so semiconductor diode. So this is just a simple diode. This is not a light emitting diode. So this is not a LED. Okay, but it's still a diode. That means it just rectifies the current. It makes sure that it flows in one way. So for example, in case of a AC battery, right, alternating current, it'll make sure that the current flows in one direction. One more thing in the symbol, the circle is optional. You can make the circle or leave it. Okay, so the
Okay.
wire that is, yes,
Yes, alternating current. Talk a little about it. Do you guys know what alternating current is? What do you understand by alternating current? Yes, Abdul Rahman.
Ma'am, I wanted to talk about those LEDs.
Abdul Rahman, can we move on, because we
Okay,
haven't even.
AC, alternating current is AC and direct current is DC.
Yes, okay. I hope you understand that, I was thinking of doing chapter 42 as well, because, only 2 days are left in your exams, in your physics exam.
Yes.
Okay, so yeah, alternating. So what do you understand by alternating current?
Alternating means it can flow in any direction, and direct current only flows to one direction. Direct current is available in our homes like switches, circuit boards.
Right, right. So also remember that alternating current moves in one direction and then in the other direction. It's like a swing, swing,
Yes.
sometimes forward and then back, not sometimes, back, forward, backward, forward,
it's like a
backward, forward,
if you look
backward.
if you look at the graph, it also looks like an oscillation
Yeah,
because
can
it
we show
keep.
us the graph, Santosh? That will be helpful.
I'm not sure where it is. Okay, yeah, here it is. This is it.
Yes, yes. So the graph on the positive side is current flowing in one direction, and then in the negative side it is flowing in the other direction, in the reverse direction, opposite direction, then again forward, and then again backward, forward, backward, forward, backward. So conventionally, if we look at it, so forward and backward, forward, backward, it's like that.
Ma'am,
Mm,
the line they are marking with T is direct current. They have not marked it. The line marked T is direct current.
Yes. 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 So I'm just showing yes. So this is rectified. This is rectified by a
no, no, no.
diode.
He's saying that this line, the straight line, is direct current. I think that's what he's saying. I don't know.
Yes, because direct
Yes.
Yeah,
current
yeah,
flows in a straight line.
yeah, yeah.
T stands for time, right?
No, ma'am. They didn't mark it. They just marked alternating current, like telling us. But I'm just telling about the direct current, like
He's just
above
saying
T.
I think he's just saying that the direct current looks like this. He's not saying this is the direct current.
But I think this is a graph of voltage against time. Okay.
Yeah, but
And so the
he's
horizontal axis is representing time. And so direct current will be when you hide the reversed direction. I mean, the negative part. That's why they have made the negative part dotted. They
yeah,
mean to
yeah.
say, yeah, so they mean to say that the negative part of the current, negative flow of the current is eliminated by the diode. But if it was there, the graph would have looked like this. But because that negative, the reverse direction of the current has been rectified by the diode, so they are representing it with dots.
Yes,
Okay,
they are
Yeah.
Santosh?
just trying to tell that negative current is only available in two. Like there is one
Okay.
pulsating current and one is variable. Only two currents are able to go like negative way. That's just
Yeah.
variable and alternating.
Yes. Okay. Okay, Santosh, can we move on with the diodes?
Yeah, so I think this is a better graph to explain what I was just about to say. So diodes make sure that the voltage, the current goes only in one direction. So you can see that when it starts going in the other direction, it cuts off the
Yeah. Yeah.
connection, and so there's
Yeah.
nothing, no voltage, and so yeah.
Yes.
And
And
then
also appreciate that this graph is representing voltage and not current. It is
yes,
representing
yes.
voltage and not current, and the magnitude of the voltage is increasing and decreasing. I mean, it is reaching zero and then reaching its peak and then reaching zero, but it is not getting negative. Meaning, what does that mean? That the current is not flowing in the reverse direction, because when it is trying to do that, the diode is stopping it.
So that's what I said. Like the voltage is like an oscillation. It looks like an oscillation.
Yeah. Okay. So how does the diode do that? By being reverse biased, right?
No, no, no. So this is so see, if this, like for example, this is forward bias, and if for example this was AC, so if I'm not mistaken, an AC current means that when one instance it's going this way and the other instance is going the other way, right?
Yeah. Okay.
Yeah. So when, for example, let's talk about instance A and B here. So for example, at A, it's going in this direction. So now the diode is fine with this current because it's forward biased. But when it starts going in the opposite direction, this way, it's reverse biased for the other current at
Right.
instance B.
Right. Right. Yes. So that's what I was saying. Yes. Okay. Okay. Move on.
Okay, so yeah, so that's it for diodes. This is just an example. So they have the battery uh like this, and we
Okay.
know that this is positive, this is negative, right? And so the positive negative align, positive negative align, and so this is forward bias. This lamp lights up. It is also acting as a resistor for this diode. uh and now when they switch the battery terminals, so now the
Yeah.
positive is hooked up with the positive and the negative is hooked up with the negative, it doesn't flow anymore.
Okay. Also mention that try to understand the symbol of the diodes. The uh this dark mark. What should we call
This
it?
band, this
Yes,
band.
this band. Yes, this band in the symbol. I wish she could zoom in, but okay, this band in the
Yeah, this one.
symbol, yeah, is the positive the positive what should we call the positive end of the diode, and the
Positive
arrow.
terminal.
Yes, and the end and the arrow terminal is the negative terminal. Okay, let's move on to the questions.
Okay.
It's 9:34. Yeah, try to buck up a little. Okay, question number 1.
Okay. Figure 41.19a shows a lamp.
Can you keep the book directly under the camera? Yes. Yes. Okay. Yes.
Okay. Figure 41.19a shows a lamp, a semiconductor diode, and a cell connected in series. The lamp lights when the diode is connected in this direction. Say what happens to each of the lamps in B, C, and D. Give reasons for your answers. Okay, so let's do B first. Okay, so in B we have a battery, a diode, and lamps, right? So we know that this is the negative terminal, this is the positive terminal, right? And over
Let's
here
start with A first. Let's start with A first.
no, A
So
is
what happens to each of the lamps in B, C, and D? Oh, okay.
yeah, A is already explained.
Oh, okay.
Okay, so yeah, so this is positive terminal, this is a negative terminal, this is positive terminal of the diode, this is the negative terminal of the diode. So we're just gonna focus on lamp 1, just forget about this side of the circuit. So if we see positive, negative, they're all matched up, and so this L1 will light up, right? So this will light up. Let's see L2. Okay, so we're gonna forget about this wire now. Positive, negative, we have positive towards the band, negative on the opposite side, opposite, negative, that means it is reverse biased, and so the lamp does not light up. Then we move on to C. Again, I'm going to divide.
Did everybody understand? Is there
Yes.
anybody who wants to ask a question? Okay, Sundus, continue.
Okay, for C, again, I'm going to divide the circuit into 2 because that makes it easier. We don't get confused. So I'm going to focus on L1 first because we have separate batteries. Okay, so this is positive. This is positive. This is negative. This is positive. This is negative. So we're gonna.
Can you mark them a little clearly, more clearly and darkly, so that I can see?
Can you see them now?
Yes. Okay.
Okay. So the positive, negative line up, the positive, negative line up, right? Because we're forgetting about this part of the circuit for now. And that means this lamp is gonna light up.
By
now,
line up, you mean to say that negative is connected to positive of diode, and the positive of the battery is connected to negative of the diode. Okay.
Just remember that opposite charges attract, so that's how they're gonna be aligned. Okay, so now we're gonna forget about the top part of the circuit, and we're just gonna focus on the lower half. And again, we have positive on this side, negative on this side, right? Forgetting about this, positive, negative. That means they're gonna repel. This is not gonna work out. That means L2, lamp 2 is not gonna light up. Okay, now coming to circuit number D. No, yeah, D. Okay, okay, we have positive on this side, negative on this side, positive on this side, negative on this side, right? Just looking at this half, positive, negative, lamp 1 will light up. We have positive on this side, negative on this side, positive on this side, negative on this side, negative, positive, does not work out, and lamp 2 is not gonna light up. Did everybody understand?
So cross
Yes.
L2. Yes.
Yeah, cross.
Okay, question number 2. Move on to question number 2.
Okay, let me just, okay. So what are the readings? V1 and V2 on the high resistance voltmeters and the potential divider circuit of figure 41.20 if A R1 and R2 equal to 10 kilo ohm. So I'm just gonna make them here. So
We cannot hear your voice.
So I have two resistors here. I'm just gonna make it here. And then we have voltmeters here. And we have a 6-volt battery here, right? And
We
they're
cannot,
saying,
cannot see your whole diagram.
yeah,
We
just a
cannot-
sec. Can you see it now?
Yes, okay.
Okay, and then we have 10,000 ohm here, 10,000 ohm here, right? And then we want to find out the voltage reading on each of these voltmeters, right? So right now we know that because this is connected in parallel with this battery, that means the whole, like the total potential difference over both of these resistors is gonna be 6
Across both
volts.
of them. Yes. It's
Yeah,
going to be
across both of these is gonna be 6 volts, right? So we're gonna use that and we're gonna find the total current that is flowing through the circuit first, right? Because we're gonna be using this formula, right? And we know that even though the voltage does get divided, the current remains the same, right? So we're gonna put 6 in. The current we don't know. And the resistance, the combined resistance is gonna be 20,000 ohm,
okay.
right?
And also I hope everybody remembers how to add the resistances when they are connected, when the resistors are connected in series. We just add them simply, right? That was done in basic. Okay.
Yeah.
Okay.
And so 6 divided by 20,000 is going to give us 0.0003. So that is going to be the total current. So
Okay,
this is going to
don't forget
be,
the units. Don't forget your units. Okay, amperes.
yeah, so 0.0003 amperes. And then we're going to use this current value to figure out the voltage for each of these resistors separately. So voltage, we don't know now for these resistors individually, right? We have 0.003 into 10,000 ohm.
So Sandus, if they have the same resistance, 10,000 ohm, and the current is also passing through both of them and is the same, so they should have.
So I should have divided by 2, right?
Yeah, they're going to have the same voltage, and they have the same voltage because they have the same resistance and the same current passing through them. So all the values are the same.
Yeah, but in the further questions, this is the method that you have to use. So I just wanted to make sure that they know the method.
Oh, okay.
But yeah, if the resistance is the same, then obviously it's easier for you to just divide it by 2.
Yes.
Yeah.
Okay.
So then we have 3 volts, right?
So what's the answer?
3 volts.
Okay. Let's move on. Yeah.
So we're gonna move on to
you
B.
try to speed up.
So in B we have R1 with a resistance of 10 kilo ohm, R2 with a resistance of 50 kilo ohm. And then you use the same technique. I'm gonna find out the total current that is passing through it. So that is 0.001. And then using the formulas separately, individually for each of these resistors, I'm gonna plug in the values. And for this resistor, I get 1 volt. And for this resistor, I get 5 volts. Do you guys have any questions?
Yeah, okay, so it's the same method, but you will just change the values, right?
Yeah,
this time it's 10,000 and 50,000, but the rest of the working is the same. Okay, move on. Yes, Abdul Rahman.
Can you explain one in parallel circuit?
Do you have a question with you?
No.
Yeah, if we come across
I can. So the only thing that's going to be different in a parallel circuit is that the adding up of these resistances is going to be a bit different. That's about it.
1 over R plus 1 over R2. And also the voltage is going to stay the same across them because when they are connected in parallel, the voltage stays the same.
Yeah, so that defeats the purpose of the question.
Okay.
Okay, so then again for C, For C, we're gonna use the same method. In this question, they're saying that R1 has a resistance of 20,000 ohm and this has a resistance of 10,000 ohm. So I'm gonna find the total current passing through it, then calculate for each of them individually. So 4 volts, 2 volts. Okay.
Yeah.
Okay. Okay, question number 3 is not included because it is from the yellow highlighted section of the chapter.
Okay, another thing, the yellow highlighted sections of the book are not included in the IGCSE curriculum. So that is why we omitted it. And I'm sure that your teachers also must not have included it. Okay, do you
Ma'am, can you show the yellow part you're talking about?
Yeah, the transistor part of the chapter. Okay, do you guys want
It's this.
did you guys want to do chapter 42 today? Because we are already beyond
It's
1
quite
hour limit.
it's quite easy. It's not gonna take a lot of time.
Okay, so those people who want to stay can stay with us, and those who want to leave can leave. I mean, you guys are free. So just because, you know, the exam is in 2 days, so we are going to prolong this this class. And so go ahead, do chapter 42.
Okay.
Start, but try to speed up. Okay.
Okay, sure. So it starts off with analog and digital electronics. So and in analog circuits, the voltages and currents can have a value with a certain range over which they can be varied smoothly. So like this, but in digital circuits, they have only 2 values. So they either have a high or a low. So like this, right? And then
Okay. Okay,
and then
so you mean to say that in the first graph they can have any value? I mean, again, these graphs are voltage against time.
yes.
Okay, so in the first graph, I mean, you can have any value from 0 to the peak. You can have any middle value. Whereas in the
Yes.
second graph, which is below it, you can have only 2 values, 0 or that highest peak. That's it.
Yeah, and this is all. This
You
is
cannot have any value in between. Okay.
yeah, and this is because of the type of resistors that are used in them. So in this, they have a direct switch. This is what we use now. We use digital circuits. We use it, so either it has a high or a low. We have an on and off button. But for analog, if you've seen those lamps, which you can alter the dimness and brightness of the bulb, then you'll understand that, you know, they have a variable resistor. So the resistance can vary from one high to one low, any point in between, and so their voltage also varies. Okay, so then we have analog meters and digital meters. Analog meters display their readings by using a pointer on a scale, and like the weight machines, the analog weight machines. And then we have digital weight machines. So digital meters display their readings as digits, like in calculators and numbers. Okay, now we have logic gates, which are used in circuits. Okay, so there are 5 basic types of logic gates, and we describe them using a truth table. So so these logic gates are used in digital circuits because they either have a high or a low. So their input is either 0 or 1, and their output is either 0 or 1. So those inputs and outputs are referred to as logic levels. So this is like a level, high level, low level. So their
yeah,
level can either
you can think of this, as the electronic language. So one means, so you can think of that one is like there is an input, like it's on the highest value, the highest possible value. 0 means off, meaning the lowest possible value or nothing, right? Yeah, so you understand this. 1, it means on or the highest possible value. 0 means lowest possible value or off.
So the one they start with is not gates. Okay, so this is the symbol. Can you hear me?
Yeah,
Okay,
you
so
have to learn the symbols. Yes, we can hear you. So yeah, you'll have to use the symbols. Yeah, come up with your ways of learning them.
Yeah, it's kind of confusing and it's kind of hard. I got really confused when I had to learn these for my exam. So so this is a NOT gate, okay? So it has a symbol of this. The way I remembered this symbol for this for my exam was that this triangle, it reminds me of an N, and then this is the O of the NOT. So you can remember it like that. And NOT gates are really simple. So they are just they just flip the input around. So if you have a 1 coming in from this side, it'll flip it around, give you a 0. If you have 0 coming from this side, it's gonna flip it around and give you a 1. Okay, so that's simple.
Yeah, so yeah, okay. So on the left-hand side is the input, and on the right-hand side you have
Yes.
the output, right? So if the input is 0, the output. So talk in terms of inputs and outputs. So if the input is 0, the output is 1. In the latter case, if the input is 1, the output is 0. Okay.
Yes.
Okay.
And then we
move on.
have the rest. We have the rest of the gates. We have the OR gate, OR, NOR, and NAND gate. There are more gates, but we're not gonna go into that for now. Okay, so the OR gate, the way I remember the symbol is that this, if you draw an R, and then if you flip this word around and then you write an O here, you kind of get the skeleton of the symbol, okay? Because these symbols are really important. Don't mess them up. They look really similar, but you have to learn them, okay? So our OR gate symbol looks like this. And the way I learn it is that if if A or B are 1, A or B are 1, it's gonna give you an input of 1. So it doesn't have to be both, but it has to be one of them, A or B,
like
because
at
it's an
least
OR
one of
gate.
them. Yeah, at least
Yes.
one of them should be 1, and both of
Yeah.
them cannot be 1, or even
B.
both of them cannot be 0. One of them
Yes.
has to be 1.
One or both of them. Okay.
So either A or B should be 1. So
yes.
remember it like that. Either A or B should be 1.
Exactly. And so this is an OR gate. Their names are thankfully just like how they work. So A or B, any one of them has an input, or both of them have an input. The output is gonna be 1. So 0 0 0 1 0 1 0 1 1 1 1 1. Right? That's the truth table that we get.
No, but you said that both cannot be 1. Didn't you
No,
say
no.
that?
So no. I said neither. It cannot be that both of them are 0.
Oh, both of them cannot be, but both of them can. So at least one of them should be 1.
Yes,
Oh, okay.
both or 1. Okay, just remember this: both or 1 for OR gate.
Okay.
You have either 1 on both, or you have 1 on 1. I hope this is not confusing.
Ma'am, I have 2 pictures. If they can help, should I forward them on group?
Yeah, sure. Yes, please. Please share in the group whatever you think is going to be useful and helpful for others. Okay, Sundus, can we move on?
Yes. Okay, so then we have a NOR gate. Okay, so for a NOR gate, neither A nor B have to have an input for it to have an output. Okay, and a NOR gate, first of all, let me just clear the symbol. So this is a mixture of OR and NOT, right? So the OR symbol with the NOT circle in front of it. So neither A nor B will have an input, only then will it have an output, right? But
Can you repeat that? Can you repeat this NOR gate?
So neither A nor B.
Okay.
If neither A nor B have an input, it's gonna flip it around, give you an output.
No. Can you please explain in terms of 1 and 0? So if neither A nor B is.
So for example, 0, 0, this is gonna give us a 1.
Oh, okay. So if neither A nor B are 0, no, I'm wrong.
If neither A nor B have an input, so neither A nor B are 1.
Oh, okay. If neither A nor B have an input, then you get an output.
Yes.
Okay. So both of them have to be 0 for you to have 1.
Yes.
So look at the truth table. We are getting only one. Like only one combination can give us 1, which is both should be 0. A and B both should be 0.
Yes.
Right. Okay.
Okay, and then these are kind of difficult. It does need a lot of memorization. Just make sure that you are comfortable with these tables. Okay, so then we have an AND gate. AND gate is the simplest one of these. So A and B need to have an input for it to have an output. Okay, so if one of them have it, it will not work. It has to be A and B having an input. So
Yeah.
only 1 and 1 will give us 1. 0, 0, 0, 1, 0, 0, 0, 1, 0.
Yes. Yeah, try to practice this a lot. Okay, try to remember them, come up with ways of remembering them, whatever works for you, and keep practicing. Okay, and you will learn. Okay, let's move on.
And then we have the last one, which is NAND. I had a lot of trouble with learning this, but if you get the hang of it, it's the simplest of all of these. So it has the symbol of and then the circle of not in it. So the way I learn it is that I keep multiplication in my mind, okay? So if we have A is 0, B is 0, then 0, 0 is 0, right? 0, 0 multiply 0 by 0 is 0. And then this circle reminds me of the NOT gate. So I'm going to flip it. I'm going to flip the 0 and it's going to give me a 1. So 0, 0, 1. And then if B.
Okay, so this can you recap the and not? Can you draw them at the bottom and then tell us how they convert the inputs? Okay, and then how will that help us in understanding this NAND? Why do we
No,
say that
that is
NAND is
that
a
is
combination? Why do
no,
we say that NAND is a combination of and not?
you can try to remember that way, but it's gonna really mess you up. I
Yeah, but
don't want
just
to do
one
that.
explanation, just one explanation, and then if it's confusing you, you can follow
No, it's
whatever
not
works
gonna.
for you.
Okay, whatever. You guys can see it. So this is and, right? So
Okay.
the input of this and A and B. So let me label these. A and B need to have an input to give us an output, right?
Yeah.
And for
What was
this,
AND gate doing again? Can you remind me what was AND gate doing?
so
It was
A and B need to have an input to give us an
okay.
output.
Okay.
And for not, whatever the input is, it's gonna flip it around. So if
So
it's
can you
0,
write
it's
1 and 1 for AND? Can you write 1 and 1 input and then output 1 so that it so that I remember? Okay. Yes.
or the other way around. But trust me, wait, I'm telling you a way that is much easier.
Okay. Okay. Go
See,
ahead.
see, when you for NAND, if they give you like A is 0, B is 1, figure out the output. The way I do it, multiply these. So think of them as meeting up in this D.
Yes.
So think of this D as a case. So they're meeting up here and they multiply. Okay, 0, 1 is a 0. So 0 moves on and
Here it
encounters this,
gets flipped over.
yes, and it encounters this not part of the gate. And it gets
Right.
flipped over to give us this 1. So just
Okay.
multiply these two numbers, whatever digit you come with, end up with here, flip it to give you that. So only okay, so 1
Can we do a few
1
examples of NAND?
okay, Yes, I'll do all of them. So okay, I did 0, 0, so 0, 0 is 0, flip it over, it gives you a 1. 0, 1 is 0, flip it over, it gives you a 1. And if I make this 1, make this 1, and then make this 0, again, it'll give me a 0 here, flip it over, give me a 1. Only will I, when I make it 1 and 1, will I end up with a 1 here, right? And then when I flip it over, I'm going to get a 0.
Yeah. Okay.
So 1, 1, 0, 1, 0, wait a second.
Yeah, 0, and then it will flip over into 1. 0, 1 will
Yes,
give you 0, flip it
yes,
over 1.
yes,
0,
yes,
0 will give
yes,
you 0, flip it over 1. Right.
yes.
Okay. Okay. Okay, let's move on.
Okay, so that was the last of the gates. Okay, so testing logic gates. So over here they have this, they made this you can say board modules for testing the logic gates. Okay, so we're gonna do more of these as we move on, but over here they're just checking if this works. So over here they have the indicator module with the LED on it. Okay, and they have a power supply. So they have one input, one output. They have the logic gate here, and this is how they're gonna test the logic gates. Now we have the logic gate control system. That means the logic gate application.
Yeah, so these logic gates are used in security.
Yeah. So for example, you have a diamond in a museum, and you have this pressure sensor here on this table, right? So as long as the input is 1, this NOT gate is gonna flip it over, give you a 0, and the bell is not gonna ring. The moment somebody takes this gem off its stand, it's gonna start, the input is gonna be 0, the NOT gate is gonna turn it into a 1, and the bell will start ringing. So that's
Right.
one application in the security system. Yeah. And then we have a safety system for a machine operator. So in this, so for example, we have, just a sec, let me set the book. Okay. So a safety system could prevent a machine from being switched on before another switch is being operated. So we have 2 switches for safety, right? So a motor will only turn on. So this is like, we're talking about an industry. We don't want a motor to just start because somebody clicked one switch by mistake, right? So there should be 2 switches that will help this motor run, right? So we have switch A and switch B and gate and a motor attached to the end of it. So when switch A and B will be on, only then will the motor run. Switch B and switch A and B, okay? And that's when the motor is gonna run. And then we have the application on a heater control system. So the heater control has to switch on the heating system when it is cold and when it is daytime, right? So we have, wait, where's the diagram? Yeah, so there's a temperature sensor. So remember, it has to be cold and it has to be daytime, right? So we need to have a temperature sensor and a light sensor. So the temperature sensor, when it gives you a 0, so a temperature sensor will obviously only get activated when there is high temperature, right? So if it's cold, it's not gonna be activated, right? So it's gonna give you a 0, and then the NOT gate is gonna flip it around, give you 1. Light sensor will give you 1 because it's daytime, right? And gate, we have 1 and 1 gives us a 1, and gives the heater turns on. So this can be used, for example, at a school in a cold country. So schools only operate at daytime, right? So the temperature sensor could give you a 0, 1, 1, and then we have the heater system on for the day. Street
So
lights.
temperature input is 0 when it is cold, right?
Yes, yes, yes.
Right. Okay. So in cold countries, when it is cold, even during the day. Okay.
Yes.
Okay. Street lights.
Street lights. And then in street lights, you have, so over here they want a light that can be turned on automatically as well as by a switch, right? Because if a technician wants to come over and check if the street light is working, it should still function. But so that street technician could the light technician could come even in the day, and the street lights automatically only turn on in the night. That's going to be a problem, right? That's why instead of an AND gate like we were using previously, we're going to use an OR gate. So this or this could have an input, and this would turn on, right? So light sensor, when it gives us a 0, that means it's nighttime. The NOT gate is going to flip it around, give us a 1. That 1 is going to go to the OR gate, and even one input will do for our OR gate, and that's going to light up the street light. For switch, it can be 1 or 0. So it does not depend on the switch. But for example, it's daytime. So this part of this switch this part of the circuit is gone. It's not functioning, right? Because the light sensor gives us a 1 because there is light. NOT gate flips around, gives us a 0. No input from here. But switch, for example, somebody switches on the lights, wants to switch on the lights, right? So then this gives us a 1, and this 1 alone will do for the OR gate, and the street lights will light. Sorry. Yeah.
So either you turn on the switch, or there should be dark, or it should be dark.
Yeah. Yeah.
Right.
And
For
both
the
will be
street lights
fine
to
too.
be on.
Yeah.
Okay. 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 Next.
Okay. The next page is sort of like exercises. So design and draw block diagrams, like the diagrams we just saw on the previous page, for logic control system to indicate how the following jobs could be done. If possible, build them using modules. So I'm gonna build modules, just like we saw on the other page. Okay. So let me draw them with you. Let me just find a fresh piece of paper.
Are these included? You guys, I'm asking the participants, are these included for the exam?
Ma'am, I don't know.
But they're
Do
really
we-
helpful.
Okay, so can we do them real quick?
I have a question.
Yes.
These yellow parts that you told, these are excluded. They are excluded from the whole book.
Yeah.
Yes. Yes.
Okay.
Yes. This is extra. This is extra that they gave for further information, but they are not included in the IGCSE curriculum.
Because I
Okay.
forgot that they told like that, and they didn't wrote this. They didn't wrote it like in the study guide. So I spent the last 2 days getting confused in these.
Oh, it's okay. It's fine. You got extra knowledge. Okay, so Sundar, can you Ishfaq,
Okay,
can you
okay.
please mute yourself?
No, I muted him. It's fine.
Okay. Okay, so how many questions do we have at the end of this chapter? Can we do those questions first, or whatever you feel easy?
I mean, both are the same thing.
Both are same thing. Okay, hurry up.
Okay, I can do a few of these if
Okay.
you like.
Okay.
I'll
Okay.
do 1 and 6. Is that fine?
Yeah, okay.
Okay, so we have, so we allow a doorbell to work only during the day. So we know that, okay, so that means we need to have a light sensor for it. So I'm just gonna make a light sensor. So we need to have a light sensor for it. Okay, and because it's a doorbell, I also want to make sure that it doesn't keep ringing the whole day, right? Just because it's daytime, it doesn't mean that the doorbell has to keep ringing. That means it does need a switch, right?
Okay.
And now it needs to be attached to a bell, right? Because it's a doorbell. So I know all of these three components. I don't know what has to be in between them now. So I need a switch and daytime. So I know that these both have to be, these both are prerequisites for this bell to work. It has to be daytime and someone needs to be pressing the switch, right? So that means the only one gate that will help me here is the AND gate, right? Because if I use an OR gate, then if it's daytime, it's gonna start ringing the bell, right? And that's not what I want. So this is, we're gonna use an AND gate here. And let me do question 6 now.
So is
Question,
that it? Acha, okay. So that diagram is done.
yeah, because it was like allow a doorbell to work only during the day. Okay, so
Okay.
give warning of frosty conditions at night to a gardener who is sometimes very tired after a hard day and may want to switch off the alarm. So since this is kind of long, I'm gonna make a list of all the things I need to keep in mind. So frosty, that means I need a temperature sensor. Night, that means I need a light sensor, right? Switch off, that means I need a switch. And then, of course, I need the alarm itself. And then a gate that'll help me with all of these. And then in the beginning of the question, it groups these frosty and night conditions together, right? Give warning of frosty conditions at night to a gardener who is sometimes very tired after a hard day and may want to switch off the alarm. So because they have grouped them together, I'm gonna say temperature sensor, light sensor, gonna keep them together, okay? And then switch, keep it separate because I don't want anything getting mixed up. And then it also says frosty conditions. That means the temperature sensor, when it gives me a 0, that is when I want the input. That means I'm gonna attach this to a NOT gate, right? So this is gonna give me a 0, and then it's gonna give me a 1, right? Then
Can you write 0 and 1 so that it's easier to understand? So cold temperature is going to give you 0, right?
yeah,
Okay. So write down cold on top of temperature for me, because I tend to forget. Okay.
okay. And then it says, give warning of frosty conditions at night to a gardener at night. So if this is night, that means the light sensor is gonna give me a 0, 2, right? That needs to be plugged into a NOT gate too.
So it's dark, right?
Yeah,
It's dark means 0.
yes.
Yes. Yes,
Yes.
Zainab. Yes, Zainab, beta.
Can you also write 0 and 1 in the previous diagram?
Oh, okay,
Um,
okay. Okay, sure.
This time
Yeah, okay, okay.
is this previous one?
Yes, I think,
Okay.
yeah.
Yes.
Okay. This is 1. Okay, I wrote it down. 1, 1, 1.
Yeah, it's 1, 1,
Okay.
1. So when the switch is on, when the light is there, then it
Only
should
then will
ring.
the doorbell work.
Yeah, it's already there. Okay, Zainab?
Okay.
Okay. I hope
Okay.
we are making sense. I know it's complicated. You're doing it for the first time. It's a new concept, and then we are trying to run through it. I understand that. Okay, but read it again and again. And by the way, I find Stephen Popple book very helpful in understanding physics. Okay, Santos.
Okay, so then the light, so they're talking about night time, so it'll give me a 0. I want to flip it around, give me a 1. And since the NOT gate can only have one input, that's why I'm putting separate NOT gates. And then we have the switch. So this could be 0 or 1. The input could be 0 or 1, right? And then I have my alarm here. So let me tick off everything I have included. Temperature, light, switch, alarm. The gate is the only thing that's left now. Okay, so when the temperature and light are giving us a 1. So this is giving us a 1. 0 or so we want to, so the thing, this is how we want the alarm to work. When the temperature is low and there is no light, so at nighttime, the alarm starts to ring. But when this switch is turned on, when this switch is pressed, the alarm turns off, right? So we are gonna
When
go
the
back.
switch is pressed, the alarm should be turned
Turn-
off.
Yes,
Right.
yes,
Okay.
because that's what the gardener wants.
Okay.
So we're gonna go back to our truth tables, and we're gonna see what. Just a sec.
So yeah, she's checking the truth table, which gate will give us the required results.
I'm so sorry for that. My table just got cluttered. Just a sec. Okay, let me share my screen again.
Keep the truth tables right in front of you so that you can easily refer to them.
Okay, so here
Yeah, keep the truth tables in front of you. Yes. Okay. So which one will we want?
Okay, so here are the truth tables. So first we're gonna make sure we know what inputs we want, right? So we want a gate that can work with one input, but will not work with both inputs, right? Because when
With
the switch
both
is turned on,
ones, you mean to say?
yes, with both in once, yes.
We don't want two ones, because
Yes.
no, we want the alarm not to work when there are two ones.
Yes, yes.
Yeah.
Is it NOR gate?
Let's see. Don't jump, because gates are really confusing. When you jump, that's when you make mistakes. So first of all, you have to make sure you know the numbers you want to get at the end. So one, if we want the alarm to work when it's 1 0, right, or 0 1, but we don't
Right.
want it to work when there is 1 1. So now that we have that confirmed, so that means we want 1 0 1, right, and we want 1 1 0. Now it's simple. We need to hunt for this in our truth tables, right? So
Yeah,
I can see
keep
that in the
keep
Nand
what
Gate.
you wrote next to the table. Can you please keep what you wrote next to the tables?
So I can see that it's the Nand Gate. Wait, let me see. Let me draw it here. Okay.
Yeah, we cannot hear you, Sundus. Your voice
Yeah,
vanishes.
just now. Can you hear me?
Yes. Yes.
Okay. So over here, so this is the input. This is the input, A, B, output. Okay, so 1 0 1. That's what we wanted. 1 1 0.
Yes.
So it looks like the NAND gate is gonna work for us. So we're gonna draw NAND gate. And so that's the gate we're gonna use for this diagram.
Okay. Okay. Yeah, okay. Let's move on to the questions.
The 0 for the switch, is it for turning off the alarm or for turning it on? Like,
So we're not gonna go into that for now. Just remember, switch, whenever you draw a switch, right next to it 0 or 1, and keep in your mind when someone presses the switch, it's gonna give you a 1, and when the switch is open, it's gonna give you a 0.
Okay, Sundus, also write 0 next to the output of NAND. The last gate that you drew, the output, show that it is 0.
Oh, okay.
Yes, here, yes. Okay. Okay, Zainab, do you have any question?
The switch is giving a 0 when it's turned on or off.
0 when it's off, 1 when it's on.
Yeah,
Okay.
right now, this diagram is showing you that when the switch is turned on, the alarm is off. See, on is represented by 1, off is represented by 0. So when you can see that the last gate's output is 0 entering the alarm into the alarm, that means alarm is off. I mean, it is getting turned off. 1 coming out of the switch is showing you that the switch is on. So when the switch is on, the alarm is off. Is there
Okay, got it.
Okay. Is there any other question?
No.
Okay, okay. Sundar, questions.
Okay, so
There are 3 questions.
yeah. So question number 1, the combined truth tables for 4 logic gates A, B, C, D are given below. State what kind of gate each one is.
Okay, please, Sundar, can you please hurry up?
Can you
Yes.
hear me?
Yes, now we can hear you. Okay.
Okay. So the combined
Okay, the combined truth tables for 4 logic gates A, B, C, D are given below. State what kind of gate each one is.
Okay,
Okay.
so we're gonna take them
Use the truth
separately.
tables again. I wish we had a flashcard. Make a flashcard of the truth table. Okay.
But you have to but you have to learn them by heart. So right now we're gonna
the
try.
flashcard
We're gonna.
learn. Okay.
But right now we're gonna try and guess, and then we're gonna check after
Okay.
we're done. Okay.
Okay.
So let's take this as one table for now. So this is our input.
Yeah, your voice is again gone.
So that we're gonna take these as the inputs right now, and then we're gonna take this as the output. So this is our table. Okay. So 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. That means that, I mean, it has to be both of these to give us a 1. So that reminds me of the AND gate. It has to be both of this.
Yeah,
right?
only in AND gate, only in AND gate when the 2 inputs are 1, do you get an output of 1. So A
So
looks like an AND gate.
So
Okay.
we're guessing A is AND gate. Let's see B. Okay, so we're gonna remove this column. 0,
Yeah,
0,
okay.
0.
Yeah, so just make sure that your mic is right in front of you, because your voice is disturbed. Sundas?
Hello?
Yes, now I can hear you. Please make sure your mic is uncovered.
Yeah, just Sundar, I think you are using HP Omen. In that case, you need to be in the front of the laptop. Otherwise, it has got filters, so it filter out all the sound coming from the sides. So you need to be on the front of the laptop, please.
Okay, now is it better?
Yes, yes, yes. Yes, now you're clear. Okay.
Okay. So I removed the A column from between.
Yes, okay, let's do B.
Yeah.
So
0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. So that means when A or B are 1, it gives us 1. And when both of them are 1, it also gives us a 1. So this, I'm guessing this is an OR gate, right?
yes.
So
Yes.
or both of them, or
Yeah.
C. Let's go to C. 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 0. So when both A and B have an input, it gives us 0, but otherwise it gives us 1. I'm guessing this is NAND, because when we multiply it, 0, 1 says 0, flip it, gives us 1. So this is NAND. Okay.
Okay, wait, I didn't understand the C NAND.
See,
Shouldn't C be NOR gate?
Yeah,
you're right. Yeah, you're right. You're right. But we were guessing right now, but it's okay. Okay, so I'm gonna come back to it and see what went wrong. But this is NOR. We have to
Again,
check
your
this.
sound is gone. Okay.
But this is NOR,
Okay.
and we're gonna come back to it and check it again. Okay.
Okay.
Okay, so for D, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0.
Okay. So only when two
So
zeros,
yeah, does it give us a 1?
right? So what gate was
Mhm.
that?
Nand Gate?
Yeah, I think this is NAND.
Okay. Okay, now let's check.
Now let's check. Now let's check for A, B, and C and D. So we said A was AND, right?
Check
Let's
from the
check.
back. Check the answers from the back. I don't have the book. Let me get the book. Beta, you guys can also check in your books. Participants, I'm talking to you.
Okay, so 1A is AND, 1A is AND, 1B is OR, 1C is NAND. Wait, 1C is NAND and 1D is OR. NOR. But that's the opposite of what we did.
We got all wrong.
No. We got the first two right, but the C is NAND, like I said before. But wait, I think you are right. C is NOR. Let me go check again.
But what made you say NAND at the first place? And can you please keep that question?
Yeah. Okay. I think whoever made me correct NAND to NOR, you got it mixed up with the other table. I think you got it mixed up with the other row. This is NAND and this is NOR. And why I said that before was because, see, 0, 0. I just when something confuses you, just make sure, just like give it like that test. Remember that multiplication thing that I told you? It just helps a lot. 0, 0.
Yeah, but Sundar, that multiplication only helps in NAND gate, right? Not in the other gates.
Yeah. But you gotta check for each gate, right? So you check if it works, then that means it's NAND. If it doesn't work, then you can go ahead, eliminate NAND from your list. Because in the exam there's no time, and then you're really panicked. Because
Right.
when I was giving the exam, I got lots of these gates wrong, and then I had to revise them, and then that's when I found my mistakes.
Yeah,
Yeah.
Nothing. Okay.
Okay, so 0, 0 is 0, and then when you flip it, it gives you a 1. 1, sorry, I'm doing C. 0, 1 is 0, flip it, give you a 1, same thing. And so the C is NAND, D is NOR, because 0, 0 is 1, 0, 1 is 0, 1, 0 is 0, 1, 1 is 0. NOR is a mixture of OR and NOT gate, right? So neither A nor B have to be with our input. That means both of them have to be 0 to give us an output.
Okay.
Right?
Okay. Let's move on to question number 2. What do the symbols A to E represent in figure 42.12? So that's easy. You got to remember.
Yeah. Do you still want me to do it? Should we move on to question 3?
Yeah. Let's move on to question number 3. Design and draw the block diagrams for logic control systems to wake you at the crack of dawn, in which you can also switch off.
This is the same thing as we did for that Gardner thing, The only
Yes.
difference is that we are going to, so
Okay,
I made the diagram for it already. So for you need a temperature, no wait, at the crack of dawn, right? So you just forget this. You need day, light, right? Switch and alarm. So you
right.
need a light sensor.
Again, your sound.
So you need a light sensor, right?
Okay. Okay.
And then there will be no Nand Gate. It's just going to be directly. I got the wrong diagram. Let me see. Should I just draw a new diagram?
Yeah. Yeah. Go ahead. Make a new diagram.
Okay.
Yeah. Hurry up a little.
Okay, so you need a light sensor. And then you also need a switch. And then you need an alarm. Right? And then we don't know what the gate in between is. So wait till the crack of dawn, which you can also
We
switch
cannot
off.
see your diagram. Okay.
Okay, so when the lights, when there is some light, which gives us an input of 1, but the switch will be 0 or 1, right? And we need a gate that will give us 1 when one of them is 1. So 1, 0, with 0 and 1, we want 1. But when it's 1, 1, we want a 0 because we want the switch to shut the alarm, right? So this is just like before, this is a Nand Gate. I'm sorry, my diagram is really messy, but this is a Nand Gate, okay? Then we have B, protect the contents of a drawer, which you can still open without setting off an alarm. This is gonna be this.
In your diagram, you did not mention the inputs and the acha. Okay, you did. Okay. Okay, yes. Okay, next.
For the drawer, protect the contents of your drawer, which you can still open without setting off the alarm. For that, I'm gonna use this security system. It's the same thing. You're gonna use the same thing. So we might have a pressure sensor, and then that will be connected to a NOT gate. So as long as there is a pressure on it, there's some things on it, it's gonna give you a 0. No bell is ring. It's gonna give you a 1. Sorry, when there are objects there, it's gonna give you a 1, give you a 0, and the bell is not ringing. As soon as the object is removed, it's gonna give you a 0 here, 1 here, and the bell will ring. And the reason why I chose this is because you can still slide open the drawer without disrupting the pressure sensor, right? So yeah, I think that's
right. So it's the same diagram for part B, right? Question number 3, part B. Right, right. Yes, okay. Jazakallah khairan Sundus. I understand that this is a very complicated and hi-fi and a new concept, and we try to run through it. But still, we tried our best. And is there any question? Please go ahead and ask.
No question, miss.
You understood everything?
Yes, alhamdulillah.
Okay, alhamdulillah. Okay, then still, if there's any question, you can ask in the group, inshallah. We'll try to manage. Okay, okay. Assalamu alaikum wa rahmatullahi wa barakatuhu. Take care.